Cool. Today we're going to move on. We're going to talk about something called a 2-3-4 tree. Once again, it's another abstract data type. Information for it, NIOF Chapter 15, Section 3. Also, right after that is going to be the second thing we're going to talk about, which is red-black trees. Doing a lot of stuff with trees. And then next week for the last class, we're going to talk about some graphs. So, what is a 2-3-4 tree? Well, it's a tree that can have, I'm just reading this straight up, more than two options. What I mean, we're going to create a new object and we're going to put more than one item in the object. Like right now, every time we created a node, we put a single value in. But what if we put multiple values in? And instead of only having a binary tree type setup where you can go left or right, we're going to have a couple of options of which way you can go. And the big picture is down here at the bottom. What if I created nodes that could store 3 values, 8 values, 10 values? Does it make searching faster? Huh? You notice with 3 values, I now have 4 pointers to go with it. So I can have n pointers, n minus 1 values stored in each. And if I'm searching for the number 28, I go, it's not less than, it's greater than, come down to this node, done. I can make sorting pretty quick, or excuse me, searching pretty quick. Looks kind of familiar, similar to what we've done, but it's no longer binary. One value, a left or a right. What we're doing today with this 2-3-4 tree, I can store at most 3 values. Okay. I can have as many as 2, 3, 4. All these different things are going to change what we've done before. All right. Like all new abstract data types, we start thinking about constructing. How do we build it? That's the first one we're going to look at. Is it empty? Can I search through it? Sure. Can I insert into it? Can I delete into it? Well, we're going to take a look at constructing because that's going to take quite a bit till we learn how to construct it. So right now, all we know is the storage of each node can be at most 3 values. Could be 1, could be 2, could be 3. All right, so I have a list of numbers, and I'm going to copy these numbers down, and oh boy, I'm going to fill up this 2-3-4 tree. So my numbers are 53, 27, 75, 25, 70, goodness, 41, 38, 16, 59, 36, 73, 65, 60, 46, 55, 33, 68, 79, and 48. And again, we're going to be going through conceptually how to do this. Oh, if we had to get into programming, that would be crazy. All right, so I'm going to come back, and before I move on, I want to mention something. And when we did our binary tree, we stored 1 value. If I used 2 rows, had a height of 2, I had 3 numbers I could store. If I had a height of 3, there were 7 numbers I could store. Well, let's see what we have going up on this one. If my height was 1, total values I could have is 3. If my height is 2, looks like I can store 12 values. 12 values, 3, 6, 9, 12. To store 12 values, I had to go to a height of 4 down here. So searching should be a little quicker. If I have a height of 3, uh, I'm going to get 3, 6, 9, 12 out of that one, 12 out of that one, and 12 out of that one, and 12 out of that one. What number goes here?
There's 48.
That row would be 48 plus 3, 6, 9. Hold on, this isn't 12, is it? I missed this one out here. 3, 1, 2, 3, 12 more. So that would be 15. Yeah, I see where I messed you up. So I would be adding another 48 on here. 63. I could store 63 values in 3 rows. What if I had an nth row? How many values would it be? Something that you should have done in pre-calc, series and sequences, and what do we got going here? Anybody got a formula? Formula should maybe work over here for 2 as well. Anybody up on your math? Plus 12 plus 48 plus I'm starting to see a pattern here. This is one less than 4. This is one less than 16. This is one less than 64. Or to the n minus 1. This is 4 to the first minus 1. 4 squared minus 1. 4 cubed minus 1. Does that work? Okay. All right. So let's construct. See what we have. First example, might have to go through this, see what we come up with twice so we can learn it. Do, 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 do. First item I'm going to add to the list is 53. Boom. Plenty of room. Plenty of room in this guy. 53. Second item I add is going to be 27. So now I'm going to have, I want to keep these in order. So I'm going to have 27, 53. Boom. Next number I'm going to add, 75. This is kind of easy. And the next number I'm going to add is 25. Boom, I'm out of room. I'm out of room when I get to 25. So we are going to, it's a shame we don't have nice terms like we did earlier 2 weeks ago when we did percolate up and percolate down, but this is going to get busted up. 25 is going to be on this side. So I'm going to bust this up now, and my top node is just going to contain the number 53. To the left, here goes 25 and 27, and to the right is 75. Next number I want to add, 70. Now, I'm going to add the 70 to the right side. I'm going to add. So we're starting to think of a process here of, I filled this. Once it's full, it's split. But now I'm going to add down. So my next one is going to be 53, 25, 27. And over here will be 70 and 75. 41 is going to go to the left side of the 53. 53 stays. 25, 27, 41. Now, what's going to happen is if I get another number on this left side, we're going to split it because this one's too big. This time we're going to move a value up. So my next number just happens to be 38. And when I come in, I go 38. No, it makes this side too big, right? 38 is going to slide in here. So now I'm going to split this guy and I send the 27 up. 27, 53. Okay. To the left of 27 was 25. To the right of 27 and between the 53 is now going to be 38 and 41. And to the right of 53 is 70 and 75. I need more paper. What numbers do I have left? I have 16, 59, 36, 73, 65, 60. I have a lot of numbers left. 68, 79, and 48. Right? And my current tree looks like this. 27, 53. And remember, I can still put another one in here eventually. 25. Coming down off the middle, it's 38 and 41. And over here to the right is 70 and 75. All righty. The next number I'm going to add is 16 from the bottom up. 16 is going to go there. I'm going to add 59. 59 is going to get added into this node. 70 and 75 are going to be pushed over. Where's the 36 going to go? We're working here, so I come in. Is it less than 27? No. Is it greater than 27? Yes. Still less than 53. It's going to come down this path. And there goes our 36. Could I quickly search and find a number? Yeah. 73. It's going to try to go into here. The dragon goes crazy and blows it up. I'm on 73. You tell me what you think it will look like after we add 73. Because this guy just gets blown up.
Would the 59 be pushed up to the top?
No. What did we push the last time? The one that was where? In the middle. It was the one that was in the middle went up, and what was on the left went left, and what was on the right went to the right of it. Still have room up there. So 73 was going to come in here somewhere. It's going to be on the right. So I'm looking at 27, 53, 70. 16 and 25, 36, 38, 41. I have 59, 73, and 75. So what happens if I put a number here in this box, like 37? What would happen? This would blow up. A number would get sent up here. This would get blown up, and we'd have to have a top node of 53 coming down to 27 on one side, and yada yada yada. 65. 65 is going to be greater than 53, less than 70. So I can still get 65 in here. 60. 60 is going to fit in there, so I might as well write this one out. 27, 53, 70, 16, and 25. 36, 38, 41, 59. I was putting 60 in here and 65. And again, you see, I didn't insert it in the beginning. I inserted it sorted. And over here is 73 and 75. So again, the way we're filling this makes for extremely fast sorting. 46. 46. Go ahead and do what you think happens to 46. Let's see. 46 would try to go in here. That doesn't work. So I blow this up and I send 38 up. 38 blows this guy up. 38 blows this guy up. 53 is now by itself again. 27 and 38, which just got sent up, goes to the right. 70 goes to the left. Still left at 27. Oh man, I'm getting pointer here and pointer there and how all these pointers connect. But this is to the left of 27, 16, and 25. I sent the 38 up. So here's the 27 and the 38, which means here in this middle goes to 36. Greater than 38 was the 41 and the 46. To the left of 70, whoops, 59, 60, and 65. To the right of 70 is 73 and 75. It's like a double blow up. Still followed the rules. Blow up, send it up. Two full at the top, break it apart. You don't know. You got the idea of what's going on? Start another one from scratch? Yeah. Let me give you a list of numbers. 70, 17, 8, 23, 31, 11, 48, 21, 19, 3. That's a 6. Let's just put that on a different line. 6, 68, 75, and 72. Example number 2. And this is just a search tree. It's no longer a binary search, just a search tree. I'm gonna give you a minute or two to try to get ahead of me. La, 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 la. First three are pretty easy. That 17 now seems to be some sort of pivot. So when I add 23, it's going to go on the right side. 17 is going to stay. 8, 23, 70. Pretty good. All right, I'll let you get ahead again. I'm going to pause to let you get ahead. All right, I'm going to add 31. 17 is happy. 8 is happy. 23, 31, and 70. They seem to be happy. 31 is good. 11. I don't have to draw a new one. I can just slide 11 in there. 48. 48's trying to go in right there, which means it's blow up time. The middle goes up. 17 and 31. To the left of 17 was the 8 and the 11. To the right of it is now going to be 23. To the right of 31 is that new 48 and the 70. 21. It's not less than 17. It's greater. So as we start to do this more and more, you almost need to talk your way through of how are you doing this. I'm trying to bring in 21. 21 is going to go down with 23. Okay, there's room, so we store it. If there's not room, we blow it up. 1731, 8, and 11. What are we adding? 21. So now I have 21 and 23, 48 and 70. 19. 19. We can squeeze 19 in this middle guy. Three. We can squeeze 3 in this guy, not have to replace it. Getting kind of full. 6. 6 wants to go here, which is the blow up, which is going to send it here. This is getting fuller, but not full enough to blow it up yet. So we're going to send the middle up. 8, 17, 31. 3 and 6. 11. 19, 21, 23. 48 and 70. Good. I hope that's what you got. So we added the 6 and we got all kind of craziness. The next number would be 68. 68 is going to go in this group. The number after 68 is 75. So let's draw the 68 one. 8, 17, 31. 3 and 6. 11, 19, 21, and 23. On our 2, 3, 4 search tree. And out here, we're now adding 68, 48, 68, 70. Man, are we getting full. 68 just got added. My next number is 75. 75 is going to try to go here, and 75 is going to cause not one blow up, but 2 blow ups. 68 is going to try to go up, and when it does, this blows up. So 17 stays, 8 comes down, 31 and 68 are going to stay up. Let's see, we try to send that up, which blows this up. So now 17 is happy. We tried to send 68 up here. Okay, 68's gone, blows this up. So 18 or 17 is happy. To the left is the 8, which was on the left. To the right is the 31 and the new 68. 48, 70, and 75. Okay, next number would go on this bottom row somewhere. And if we have to blow it up, it sends it up. If we have to blow it up now, we could send it up another level if we had to. Okay. Questions on 2, 3, 4 trees. 2, 3, 4 trees. All right. Sounds good to me. Using a lot of ink today. All right. The next thing is called a red, R-E-D. I was doing the B early. A red black tree. And a red black tree, again, it's not a binary search tree. It's just a search tree. Mhm. So we just did that 2, 3, 4 tree, and a red black tree is going to be extremely similar, except it's a binary tree. The last one was just search, but when we do this red black, I think I said it's not binary. It is binary. The one we just did, looks something like this: 21, 34, and if I actually drew the 3 empty boxes for each one, which means I had 3 boxes here. I had 3 boxes here. 2, 3, 2, 3, and possibly 2 out here and 1 over here. All of a sudden, I have 18, 19, and 20. And this could be something we just ended up with 37 and 40. It's not the cleanest. I apologize that. 37 and 40. Nothing's here, so nothing's going to be to the right of it. But if I have something like that, okay, this is again a 2, 3, 4 tree. A red black tree is going to be similar to it, but it will look like this: 21, 19, and I'll show you what all this is in a minute: 34, 18, 20, 25, 37, 40. Now, here's what's going to be interesting about this. Boom, 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 boom. And that's the end of the reds. The blacks: black, black, black. Tell me what you think. What's the correlation there? So what do we have? We have 2 kinds of links. And of course, we can't do this on the computer. We'd have to somehow keep track of color with each one of these. Okay, we have a red one and we have a black one. What do you think the red signifies? Reds are, let's see, 18, 19, and 20 have reds. 21 and 34 have reds. 37 and 40 have reds. Anybody?
Evens and odds.
No? Here's 18, 19, and 20. Here's 18, 19, and 20. 21 and 34. 37 and 40. Red signifies siblings. Red signifies siblings. Black is parent child. Oh, so they are the same. 21 is a parent to these guys. 34 is a parent to 37. And 34, excuse me, is a parent to 37, whose sibling is 40. Okay. So some observations. All right, just a couple of notes. So if I start at the root and go to a leaf, one black, one black, one black, one black. Ah, if I had another row of numbers up here, another row of bunch of stuff, we'd have two blacks down to every one. Okay, so there will every so a little note, every path from root to a leaf has the same number of blacks. Up level, these two are siblings, but we're only going down one. Another note is you will never see two consecutive reds. You'll never see a red because we start going down different levels. Okay, so we got the idea, we got the overall. Now we need to build one of these. And the way we're going to build one of these is we're going to build this and mirror this to see how it goes. Because at some point, when we blow this up and it goes up, it's going to change some things the way this is laid out. And in terms of programming, oh boy, yeah. Okay, let's see what we have. Blah 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 blah. Do you want to do another one? Get over here. Um, here we go. Here we go.
Professor Faringer,
Yes.
could I copy down those notes real quick? Um,
Yep.
on the previous page, please.
Sure.
Could
I'm
you?
glad to hear a voice. So there's two kinds of links. Reds are sibling, blacks are parent child. Every path from the root, 21, to any leaf has the same number of blacks. And because we have two levels here, we'll only have one black going down. If we had a third level, we'd see two blacks. And you'll never see two consecutive reds. You can see how the reds will always follow. Yeah.
Thank you. I'm good.
That's excellent. All right, let's take a couple of numbers and see how we go. Numbers are example one. The numbers are, here we go, 53, 27, 75, 25, 70, 41, 38, 16, and 59. Of course, this is much easier on taking 3x5 cards and sticking them on a whiteboard and having a red and black marker. That's great. Here will be my red black tree. First number is 53. Second number is 27. Third number is 75. So I did the first three numbers and I'm going like, okay, yeah, I got that in red black. I got it. 53 is here. 27 is to the left. And 75 is to the right. And how are each of those connected, red or black?
Red.
Red, yep. And you notice there are no blacks, which means these are all still the same level. If there was one black going down, I'd have two levels. If there were two blacks for each level, I'd have three levels. All right, the next number that comes in is the 25. And that's going to cause us some problems. So here goes 53. Off to the right is 25 and 27. Excuse me, the left. Off to the right is 75. So if I'm adding a number, here's my 53. My 27 is still here. 75 is here. But when I add the 25, it's going to be to the left of 53, to the left of 27, and go out here. These two are siblings, 25 and 27. And these two are blacks. 53 is on its own level. 27 and its siblings to the left. 75 has no siblings. So when we added that new 25, it looks like this red now changed both of these to black. What would the patterns be that you would slowly pick up of how to change these? All right, that was 25. Next number is 70. So now I have 53 hanging out. I have 25, 27. I now have 70 and 75. 53. We had 27 here. We had 75 here. Here's 25. Okay. We're now adding, we just added 70. So 70 should be the left of 75. 25 and 27 are siblings. 70 and 75. And then, of course, we have black and black. Next number is 41. I think we can squeeze 41 onto these two graphs. 41 in this case goes to the left of 53, and it'll fit in this node. 41. 41 is less than 53, greater than 27, which is nice because when I put it in, it's a sibling, and I just added a red. Do you notice I added a red? And it's like, remember, we can't have two reds in a row because if we had two reds in a row, we'd have to switch and do the blacks. That's when the blow up occurs. So when I'm blowing up here, it would be the same as having reds in a row over here. So we just added 41. Okay, 38. 38 is going to cause a blow up. 38 would be 53 greater than 27, less than 41. So 38 is going to go over here. When I add it, it becomes a red and all, it blows everything up. So let's see what happens when 38 is added. I will give you a minute to work on that. I added the 38, so the middle one in this node goes up. Over here, I had a 25 all by itself. In the middle here, I now have the 38 and the 41, which were the two numbers to the right of 27. And I have 70 and 75. Now let's look at this one. If I try to add, okay, so I'm starting to get patterns. I'm going to add a number according to this, the way this is laid out. When I add it, it becomes part of that node. So, hey, 38 wants to be a sibling here. 38 can't be a sibling with 25 and 27. Oh, so what's going to happen here? 38 wants to be a sibling. But now I have two reds in a row. Again, 38's trying to get in here. No, 38, you can be a sibling to 41, but not all of these. And when I make that, so this now became a red, which now results in this becoming a black, this becoming a black. Oh, so I'm starting to try to figure out how all this works. Right now it's red. Let's write this out and see what it looks like. 53, 27, 25, 41, 38. Back to being a binary tree. 75, 70. Okay, shouldn't have drawn the lines in. This became a red. 38 and 41 are siblings. 70 and 75 are siblings. 27 and 53 are siblings. I have one black, one black, one black. 27 and 53 were siblings. 38, 41 are siblings. So let's see, when I added this red, it went crazy and said, change both of these next level to black and change it. So it went, okay, I got two reds in a row. It's kind of says, go up and switch all of those. Switch these two reds to black and that black to red. So as you're doing this, you start to figure out how to do it. Then you start talking yourself through patterns and say, okay, is that what happens every time? Now I have two reds in a row, which means every level on this subtree above it gets changed. Hmm. Hmm. And we do one more that we do? Sure. List of numbers. Example number 2. 50, 25, 75, 37, 68, 49, 42, about 70, and 76. Oh, I'm so sorry. There it is. I'm gonna pause the record. Right. As always, the first three numbers are easy. If something that looks like this. Did the 50, did the 25, did the 75. They're all siblings. Well, 37 wants to join the party. 37 wants to join the party, we blow up the root. Over here, we had the 50, 25, and 75. Now 37 wants to join. It's less than 50 and greater than 25. This had been a red. This wants to be a red. So it blew stuff up. It blew it up. This,
Professor Faringer,
yeah.
I have a question. I thought the 37 went on the left of the 50
Oh crap.
because
It's
it's
all,
less than.
yeah. Cross this out, cross this out. Make this 37 over here. My bad. 234 is now right. This is still right. 37 and 25 are siblings. This is now black. And you remember last time when we were talking our way through it, it affected the one side but not the other. So there's lots of things, you need to go through all these situations to figure out how this is going to work. What patterns do I pick up? This course started with, and we need to look at test data more and more. That was our first blow up. Next number we're adding is a 68. 68 goes over here, and we do not have two reds in a row, so that's happy. We just added 68 here. That's my first mess up in like 3 weeks. Gonna add 40. 25, 37, and 40. 68, 75. I had 50, 25, 75. Over here was 37. Over here was 68. And we now add 40. Where do you think 40 goes? You're going to love this, folks. It goes to the left of 50, to the right of 25, to the right of 37. So 40 is now sitting down here. Oh, I know that this is still a black. This is, in fact, a red. That's good. 25. This is still black. What happens here? Yeah, you were muted, Nicodemus. Sorry.
You're going to
Well,
get two reds. You're going to have to shift
Yeah, we're
40
gonna
up.
get two reds in a row. So what's a way to solve this? What would be a way to solve this? I mean, I want three siblings here. These are all three siblings. How could I solve this? Something we learned before. 50, 37, 25, 40, 75, 68. I shouldn't have started. 75 and 68 are still siblings. 50 over to here is a level. This, what did I do? Yeah, I got two reds in a row. So I did a Adelson-Velsky type left rotation. Really? Yep. You can see we're getting the basic instruction of how these bad boys work, but you'd have to do lots and lots of test data before you could actually code it. But this is just another data type. Lots and lots and lots of data types. Huh. It's one black on all the paths. Siblings are red. Looks pretty good. Nice. What is that? Another example. That's so many examples. Okay. So the last thing, we just talked about a 2, 3, 4 tree a few moments ago. And we looked at what if it's a binary tree? And we talked about, you know, for a height and for a height of 1, I could store 1 item. When I came down the next level, I could store the 1, I could store 1 item. Here I could store 3 items. Here I could store 7 because I would do 2 dots off of each of those, and so forth and so forth. If M was 4, I can store n minus 1 items. So 3, 15, 63, 75. We looked at that list of numbers as well. Here's 10. What if I could put 10 things in each node? 9, 99, 900. Oh boy. And again, we looked at some pre-calc type sequences stuff. If I give you 10, how do you give me that? Here's 100 items. I love this. Empirical studies have shown that the best is to go anywhere from the range of 50 to 400. Well, you'd be storing lots and lots of data, wouldn't you? Okay. Once again, not a big fan of lecturing for an hour and 6 minutes, but we had to cover all this today. Um, questions? Questions? If not, we have one class left, and that is next Monday. We will be talking about graphs, some cool stuff with graphs. All right.